What's going on, everybody? This is Mr. Diamond, and we are going to be doing our decomposition example problems. So the first thing I want to point out before we even start these, we know they're decomposition because I just told you that they're decomposition reactions. But if you were in a situation where you were looking at these on a worksheet, because just like naming, some of the problems will come when these are mixed together. Decomposition are the easiest to identify. You'll notice that each of these types of reactions only have one thing. Now in this case, we have compounds for each of them, but there's only one element that's actually, or one compound that's listed in the explanation of the problem. H2SiO3 decomposes. LaOH decomposes. Iron 3 fluoride decomposes. All of those are also easy because they have decomposes in the name, but don't get used to that. There's a bunch of other ways I could word it, like breaking down, or I could just give you H2SiO3 arrow and you would have to predict it. So easiest to identify are going to be decomposition because they're only going to have one thing on the left side. Now let us begin. So we have H2SiO3 right away. We can start by writing H2SiO3. I do also have a pencil close by. Remember, like I said, with balancing, whenever you're doing this on paper, you probably want to use a pencil for that, but I'm going to use a pen for my actual formulas. And we know it says decomposes, so we're going to put an arrow. And here is where you have to figure out which of the synthesis reactions are you looking at. Just to make sure that we remember, the types of synthesis reactions we had dealt with were ionic compounds, covalent compounds, oxyacids, and a metal hydroxide. Those are the four types of reactions that we had for synthesis. When you're dealing with decomposition, though, there's actually only three things you have to worry about. There is two types of compounds that you'd have to worry about, metal hydroxides and oxyacids. And then there is just binary compounds, things that are only made out of two pieces. If they're only made out of two pieces, they're a lot easier. In this case, we have to guess this is not made out of only two pieces. Is this an oxyacid or is it a metal hydroxide? And it has an H out front. That means it's an oxyacid. Okay, so what does that actually tell us, though? Well, when we did synthesis reactions, we said that oxyacids were formed from water plus a non-metal oxide. And if you remember, the way we solved them was we just mashed everything together. We took all the pieces that we had, added them together, and kind of shuffled the order just a little bit. So we're going to do the opposite of that. We know that we have to make water and a non-metal oxide because that is the thing that we started with when we made a oxyacid, or an acid that had O's at the end. So now we're going to do the opposite of that. We're going to pull out water. We know water must be a piece. So these H2s went over here, and also one of the O's. And then you just have to list whatever is the leftover amount of stuff. There is a couple of times where it'll be a little more complicated than that, but for the most part, you're really just going to be pulling out water and then pulling out the other piece. So leftover after the water, I have Si, and then I would use one O, so it'll be SiO2. And then because of the fact that you just separated apart one compound into its pieces, you didn't do crossing, you didn't do anything like that, we have two H's, we have two H's, we have one Si, we have one Si, we have three O's, we have 1 plus 2 is 3 O's. We are balanced. Okay, the next one is the hardest type of decomposition you can have. We have LiOH. It's not two elements. That means that we have to be dealing with either an oxyacid or a metal hydroxide, and it should be easy to tell them apart because there's no H out front, and this is a hydroxide. OH is hydroxide. So we're going to start with our LiOH. We're going to put our arrow because it's decomposing. And then if we remember back to our synthesis reactions, metal hydroxides come from metal oxides and water. So one of our pieces must be water. We have to have water. But last time we just separated them apart. This time we actually have to do a little bit of work. So we have water, and then this other piece, based on what we talked about in synthesis reactions, needs to be a metal oxide. So we have to look back here at our formula. Which of these pieces is a metal? Well, it's got to be the thing listed first. And if we check the periodic table, Li is in fact a metal. So I'm going to do my work up here because I have more space up here. So we've got Li as our metal. Because that's a metal, we're going to have to make an ionic compound, which means we're going to have to cross our charges. So Li, looking on the periodic table, has a 1 plus or a plus 1 charge. We also need to make it a metal oxide. And oxide, hopefully you've got enough practice. LiO is what we're looking at. O for oxygen is oxide. Oxide has a 2 minus charge. Then we're going to cross your charges, and we'll get Li2O. That can't be reduced. There's no states of matter, so we have our full formula. Now, in this one, we do actually have to do some balancing, but it's pretty easy balancing. I have 1 Li. I have 2 Li's. So let me put a 2 there. I have 2 O's. I have 2 O's. I have 2 H's. I have 2 H's. So we are balanced. So just a little bit more work. The next two are actually the easier of the categories of them. We started with the hardest two. We're now going to do the easiest two of decomposition. This one's just a little bit harder, though, because we first have to figure out what iron 3 fluoride is. So first, iron. Iron is Fe. Fluoride is F. There's quite a few people who made that mistake on the last test. Make sure you're double checking if you're not 100% sure what the formulas for them are. Iron is Fe, not I. Fluorine is F, not Fl. Fl is fluorovium, which is way further down on the table. Anyway, we need to figure out what type of compound this is. Iron is a metal, so that means we're dealing with an ionic compound, which means we're going to have to cross our charges just like we did up here. Iron is in the section of the periodic table that does not have only one charge, so we need to figure out what charge it has. And to do that, it's going to just be this. It's going to be the Roman numeral that it was given. So in this case, it's a 3 plus. Fluorine only has one charge. It's a nonmetal. It's one step away from being a noble gas, so it's going to be 1 minus. And then we'll cross our charges. Okay, that now gives us our first piece. We will have FeF3. That is our first part of our reaction. Now, for the second part, you don't actually have to think about the synthesis reactions, because the synthesis reaction tells us that it was a metal and a nonmetal, and they made a ionic compound, which we made right here. But because decomposition reactions are only involving splitting things apart, if we look at the formula, if you have Fe and F, you only have two things. What is the only possible way you could split them apart? Well, the only possible way you could split them apart would be if you put an Fe and you put an F. Now, don't stop there, though, because remember, these are both alone, so we need to double check. Is Fe one of the really needy elements? Is it one of our diatomics? And no, Fe is not, but F is. So we want to make sure that when F is by itself, we put it as F2 unless we have a very good reason not to, and we don't in this case. Then we get to go through and we get to balance. We have 1 Fe, we have 1 Fe, we have 3 Fs, we have 2 Fs. I'm going to have to go with the least common multiple here, so I'm going to have to do 2 and 3. Then I have 2 Fes, I have 1 Fe. I'm going to put a 2 out front. And then just to double check, nothing goes into 2, 2, and 3. All right, last example, even though it's a little bit different, we have water, which we all hopefully are still comfortable with. Water is just H2O, and it's breaking down, so we're going to put our arrow. The only thing that's different about this is that we know what water is. Yes, it's a molecular compound, so we know it's made out of H's and O's. Neither of those is a metal, so we didn't have to do crossing of our charges. But it's going to follow the same approach we did up here. There's only two elements. There's only one way that you can separate two elements. You can separate it into H's and O's. And then again, you just have to double check. Is H one of the needy elements? Yes, it's a diatomic, and O is also a diatomic. So we'll have to put 2's there. Then to balance it, we have 2 H's, we have 2 H's, we have 1 O, we have 2 O's, so we'll have to put a 2 there. That means we'll have to put a 2 there, and then we are balanced. Now, if that makes sense to you, but you are easily confused, you don't need to pay attention to this. I just want to clarify for those of you who care a lot about science or plan on taking later classes, this is not actually what will happen. And in fact, there's been a lot of times on these chapters, like this last chapter, this chapter, and for the rest of the year, where we're really oversimplifying things because it's important that you understand the rules as opposed to just being able to memorize what the facts are. This is also why Googling certain answers for questions on worksheets and tests really doesn't help you as much in this class. because of the fact that there's like usually more scientific accurate ways of predicting what their name is going to be. Or in this case, water would actually probably split apart into H and OH. But you would never write that answer. You would never predict that answer. Based on the rules we have discussed in class, which you need to be able to learn so that way we can explain why the rules get broken or where they work differently, is that if there's two elements, the only thing they can do is split apart. You can get H and you can get O. They're diatomics, and then we balance. All right, that's going to be it for this video. Decomposition, a little bit easier than synthesis, but they're still the toughest of all the reaction types, those two of them combined. The next video we're going to be watching is going to be notes over single replacements or double replacements, and then the examples for those are going to go a lot more work, but a lot easier to solve. There's a lot less thinking involved in the actual figuring out what they are process. In the meantime, though, if you have any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.